All right, we're into chapter 2 today. And chapter 2, well, the title of it is just called derivatives. So in chapter 1, we looked at what a derivative was and the whole idea of secants and tangents. Chapter 2 is now that we have an idea of what a derivative is, how can we calculate them? So how do we started doing things with first principles, right? So we were able to do that. But even with first principles, we were making relatively simple calculations, right? We didn't, what was the biggest one we tried? I think a cubic. We didn't try anything bigger than that. We didn't try anything that was sort of a function of a function or anything significant with rational expressions. So we need to start looking at things that become a little bit more difficult. Today, we're only doing polynomial functions. We're actually not adding very much, but it's kind of a funny chapter because almost all that we do in this chapter is just keep taking derivatives of harder functions and then what we can do with them. Today's the day, though, where we look at what these shortcuts were. So if you're still not positive on the shortcuts that we had done, this is where you'll see them. So these are kind of the 5, I guess, that we're going to use from now. It says the constant rule. So if you have a function and it's just equal to a number, just to a constant, then the derivative of that function would just be 0. And that makes a lot of sense, I think, because if you think of what the graph would look like, if it's just equal to a constant, your graph would look like that. It would just be a horizontal line. And of course, the horizontal line would have to have a slope of 0. So that makes sense, I think. The power rule is the one we were basically looking at in the last little bit, which is what some people notice. So notice here, it's a function of x, and that n is just representing where a number will go. So if we take the derivative of that, the rule was that we pull down that exponent and multiply it out front, and then we decrease the exponent by 1. So the derivative would look like that. And I think that's the one that most people had noticed already. Multiply in front by the exponent and then decrease the exponent by 1. The sum rule we used as well. The way the sum rule, and for that matter, the difference rule underneath, if you want to take the derivative of something where you have 2 functions added together, you just take the derivative of each piece. So that one's not too bad. Same here. We would just subtract them. And remember, these are officially the rules. Sometimes it's easier once we actually see the examples to understand what they mean. And then the constant multiple rule. C is just a constant again, it's just a number in front. So f prime of x is just equal to c times g prime of x. So if you have a number in front, you just multiply it. And I can show you probably a simple one where that's an example of. We're going to try some more in just a second, but if f of x is 6x cubed, we'll say, then that's kind of written as f of x equals 6g of x. I'm thinking way too complicated about this, right? This is a very easy derivative, but this is basically what that constant multiple rule is showing you. So f prime of x is 6 times g prime of x. G of x, I should say, was just this x cubed, right? So our derivative is 6 times the derivative of x cubed, which is 3x squared. And now you can see what actually happens. That 6 and the 3 get multiplied to get you the 18x squared. Now, we do that in one step, right? We would have gone back here, and you would have just multiplied the 6 and the 3 right away and decreased the exponent by 1. But really what we've done then is we've used that constant multiple rule and the power rule and put those together to get those derivatives. I just want to try a couple, and then we're going to try one example, and that's enough. That's all we need to really do today. A lot of this I think you already knew. Here's our function. It's quartic, but most importantly, I guess it's the sum and difference of a whole bunch of functions. So all we have to do is take the derivative of each individual piece. So the 5x to the 4, you multiply the 4 by the 5 to get 20, and then decrease the exponent by 1. Minus 7x cubed, multiply the 3 by the 7, decrease the exponent by 1. Notice I just left the minus there, right? And then I suppose it kind of gets, I don't know, I don't think it's harder. The next one is plus 2x, and the derivative of that is just 2. Here's one of the reasons you can think of it. If I wrote it this way, it would be 2x to the 1, right? We never write that 1, but we could. When I take the derivative of that, 2 times 1 is 2. My new exponent would be 0. And anything to the 0 is just 1. So it would be 2 times 1, or just 2. That's not a part that you'll have any trouble with. If you have a linear term, the slope is just, or excuse me, the derivative is just the number in front. You can think of that graphically too. You think of the function 2x. That's linear with a slope of 2, right? Well, if it's linear, you're looking at it, you know the slope's 2, and that's what the derivative is supposed to find, right? So you get 2, just the coefficient. That didn't work. Nope. And then the next one is that minus 6. And the derivative of constant we said was 0, right? So we could put a plus 0, but we never do, right? No point putting a plus 0. So we're done there with the plus 2 at the end. F of x equals the cubed root of x. This is one that we considered the other day when we were talking about places where we couldn't take the derivative, right? This function doesn't look like a. It doesn't look like a polynomial. It's not a polynomial function. But what we can do is we can rewrite it so that it at least looks more like what we had before. If we have the cubed root, that's the same as writing it as a fraction of 1/3. And if I do that, now I can go ahead and take the derivative of it using exactly the same idea. You take the exponent, the 1/3, and you'd multiply that in front. So the 1/3 goes there. X stays, and the exponent is supposed to decrease by 1. So we're going 1/3 take away 1. Which is minus 2/3. For some reason that tends to cause some problems, so just a little heads up on that. So our new exponent is minus 2/3. Now we should actually have an idea of what that means. A negative exponent means you're supposed to flip it down into the denominator. So it would look like that. And an exponent of 2/3 means take the cube root, because the 3 right here in the denominator tells you what root to take. And the 2 up top means you're taking the cube root of x squared. And so that's our derivative right there. Not one that we would be interested in trying to do by first principles, but we can do it that way not too badly. Now you may remember when we were talking about places where the functions were non-differentiable, and this is the graph that we did just the other day. Sorry, I'm talking about all kinds of things actually. I thought this was going to be a really short lesson, and now I just keep talking. That was this function right here. And we said it was non-differentiable right at x equals 0 because you had a vertical tangent. And you can actually see that now because here's our function. So if we tried to calculate the derivative at x equals 0, you'd end up with 1/0. Right? You'd sub in 0 for x and get a 0 on the bottom. So that was the problem in the last one. Let's just do this. There we go. f of x equals 3 over x to the 5th. Once again, a question that we really don't want to do by first principles. But we can take sort of the same approach we had with b. If we rearrange that and bring the 5 up to the top, you bring it up to the top as long as you make it a negative exponent. Kind of like we did in the last example, right? We had a negative exponent, we dropped it to the bottom. So now if I take the derivative of this, the 3 times minus 5 gives us a minus 15. Be careful with the exponent. The exponent has to drop by 1. So it's minus 5, take away 1 more, which is minus 6. And I guess we could simplify that a little bit and just write it with a positive exponent. We should try and write with positive exponents when we can, especially when it's a simple function like this. There's your derivative. So we did pretty good there. We handled examples with roots. We handled polynomials, which you're going to find relatively easy. And then in situations where you have a variable in the denominator, just use a negative exponent to bring it up to the top. Okay, last one for us. It's this is now a problem at least. It's a cubic function, and it says determine the location of all horizontal tangents on the function. So in a cubic, remember a cubic could look a couple different ways. Our simple x cubed graph looked like that. That was how you were introduced to it in grade 11. But we also know that a cubic might look like that, or vice versa, I suppose. So there's a couple different possibilities for horizontal tangents. That red one just has a single horizontal tangent going through the middle, actually. And the red one, or excuse me, the blue one would have 2 horizontal tangents. So we're not exactly sure what situation we're in just yet, simply by looking at the equation, but we're going to figure that out. The key to getting horizontal tangents is right there, the derivative would have to be 0. Right? If we're going to get a horizontal tangent, the derivative is 0. And that's something then that we should be able to find. So we need to take the derivative. You're going to find that almost every example we do from now until the rest of the year is step 1, take the derivative. Not every time, but a lot. So if we take the derivative, we get that. We want to know where horizontal tangents are, so we're going to set the derivative equal to 0. And that's not the nicest looking example, right? We've got a quadratic equation now that we have to solve. 3x squared minus 4x minus 5 is not a simple trinomial. There's 2 ways to solve these, right? You can either solve them by factoring, which is the faster way to do it. And if factoring doesn't work, you can use the quadratic formula. If we were going to try and factor it, we would need 2 numbers that multiply to minus 15 and add to minus 4, which isn't going to happen. So we are going to have to use the quadratic formula by the looks of it, which is probably good for us to try and remember. I imagine you've got it by now since on the test it's been there a couple of times. So there's your quadratic formula. Remember, what we were trying to do is we're trying to find the places where this function might actually have a horizontal tangent. Oh, and what do we get there? 76 over 6. And what, 76 can be reduced, can it? So I could write that as 4 plus or minus 2 root 19. That's not a very nice answer. But I don't think we care too much really, because we're kind of done at that point. Therefore, at x equals 4 plus, whoops, slide 2. So at those two values of x, that's where we get horizontal tangents. Now, in this example, the question itself, let me scroll back up there, said determine the location of all horizontal tangents. And I guess there's a little bit of ambiguity there, I would say. Often I'll say determine the location of the points where it's a horizontal tangent, and that's not what we found, right? We've only found x values. So technically, what we could do from there is probably convert those to decimals, and then you could sub those values back in to the original function up there to get the corresponding y values. But I really don't want to do that, so we won't. I will try and be really specific, though, on tests and assignments on what I want you to do. So I'll either say determine the location of all points, or I'll say determine the x coordinates of the points when you have a horizontal tangent. So I'll do my best there to make it as obvious as possible what I need you to find. Okay, so there you go. That is sort of your basic derivative stuff. We'll have lots more that we need to do with them, but a lot of it sort of falls back to this basic principle. And if we can take the derivative of these functions, we'll be able to base everything else on that.